you will get lots of practice doing free body diagrams because every single problem you're going to do pretty much until January will involve a free body diagram.
Hold on, so making a free body diagram isn't like the whole problem?
No. It's just one of the skills that you build
I was kind of hoping
to be able to solve. Now, I will give you a FIP where I will ask you, you'll have one question where you have to just draw a free body diagram of the following situation. Oh no, it's trig. That's coming. The trig's on its way. Just wait. You know, if you're missing trig in physics, just wait. Like if you don't like the weather in Ohio, just wait. Okay, so this is this idea that we've got here. Actually, you know what? Let's go back because we'll do the practice with the Fourier problems. So if you would be so kind as to get out your books, turn to page whatever it is that's got section 4A, and you all pick up a Fourier worksheet on your way in. We're going to start with some problems. 140?
4B12.
Oh, that's 4B. You don't want to start 4A. Okay. Let me check something real quick here. Okay, you know what? We will, sorry. We will do a little bit of discussion first, I guess. I forgot where this all fell. Okay. If we look back to our force diagram that we made of ourselves sitting in the chair, we've got the force of gravity acting down on us. We've got this thing I told you about called normal force acting up on us. If something is, sitting on the surface of the earth, as long as the forces on it are all balanced, it's going to continue sitting right where it's at. You're sitting in your chair. You're being acted on by gravitational force and normal force. As long as nothing changes in that balance of forces that's acting on you, don't go anywhere. If I come along, again to go back to our shoving, if I give Devin a good shove and she topples out of her chair, we know that an unbalanced force is acted on her or she would not have moved. So this is inertia. This is Newton's first law. Inertia is useful in explaining lots of things as philosophical metaphor, but in a physics sense, we're just saying that as long as the forces are balanced, things are going to keep doing whatever they're doing. So let me ask you this. If I have, in a frictionless vacuum, a ball of some mass rolling along the ground, it is rolling at 100% constant velocity. It's not slowing down, it's not speeding up, it's not accelerating in any way. It's moving though. Is that a demonstration of inertia? Yes, it is. Because the forces on this ball are obviously perfectly balanced. It's not slowing down, it's not speeding up. As long as all forces are balanced, you're going to maintain your motion or lack thereof. That's inertia. It's Newton's first law. Object at rest remains at rest. Object in motion remains at motion until acted on by an unbalanced force. In the vacuum of space, where you've got no friction, no air resistance, the only force that can act on things is gravitational attraction. We take you out on the space shuttle and we stick you outside the space shuttle on a spacewalk, and we go, boop, and flick you. And you start to float away. Guess what? You're just going to keep floating.
Wouldn't you have to actually push it?
Doesn't take a whole lot in the vacuum of space. So, you start your motion, well, except for the whole, dying lonely in the void of space in your spacesuit thing. But, yeah, other than that, It sounds really neat. When something is not accelerating, we know immediately that the sum of forces on it is 0. That's going to become so important because that's going to become something that you use to solve problems. You can sum forces, of course, on the x-axis and on the y-axis. So right now, where you're sitting, with your butt parked on the chair, on the y-axis, what is the sum of forces on you? 0. As long as you are not rising up into the air or plunging down towards the center of the earth, the sum of forces on you on the y-axis is 0. Now right now, you're putting forces on you on the x-axis, which is fine. So right now, okay, so for you, sum of forces on the x and the y are 0 because you're stationary. Start doing this, suddenly we've got some force on the x-axis. There's a little bit of y towards the end of that swing too, but that's okay, we'll disregard it. You know, we could take you in your desk and shove you sideways,
Oh, no,
Some of-
Miles, no.
but you're on the tape
We're
line.
not doing the Z yet.
Z-axis.
Oh God, no Z's, no Z's, no Z's. We're never gonna do the Z in here, ever, I promise.
Miles, stay, get out
The
of here.
Z makes my brain hurt.
It's like, what's going on?
Um,
You don't even know.
As long as you stay on the surface of the earth, y-axis sum of forces is 0. I know it sounds really simple and I'm stressing it way too much. Come on, Rosa, we got it. Trust me, you're going to come back to this again and again and again. Okay? We get to resolve and we get to resolve vectors again.
Oh,
I know you're happy. I know you're excited. Try to contain your
Well,
enthusiasm.
we already know how to do this.
You already know how to do this, exactly. And all you're doing is instead of doing velocity or acceleration now, you're just doing forces. So it's not that bad. It's really not.
it's not
This is the kind of so we can have a whole bunch of forces acting on an object at the same time. You know that, simultaneous forces. As long as they're balanced, perfectly balanced, and the net sum of net forces is 0, the thing isn't moving. Let's imagine a scenario. I'm going to take Miles and Justin and Joe. Who would be my other candidate? Who would be my other candidate? Okay. Miles, Justin, Joe, and Ethan. We'll just take that square. I'm going to give each of you a rope. Okay? That rope is attached, each of them, to a box.
like a separate box.
Nope, one box. 4 ropes coming out of each side of that box. And I'm going to set you up with this thing, and off we go. You each get to pull. So, do you feel like the 4 of you are evenly matched for strength?
Miles is good.
Strength or mass?
I was gonna-
Strength or mass. I mean, that, you know, because mass is something you can count on here. You can just lean on that rope. Who's going to win?
Miles.
Okay.
Miles got it.
I don't know what your masses are, your relative masses. So,
I mean, it's not obvious though that he's.
well, Miles seems to
You're
have
so
a bit
mean,
more volume. He's a big guy. He's a really tall guy. So I'm guessing that there is mass to accompany that volume, assuming that he's got a similar density to the rest of you. So most of you are about as dense as water. You're mostly
Oh, I was
water.
thinking mass.
No, you're mostly dense as water. So if you have similar volume to somebody else, you probably have a similar mass for them, because your densities are probably about the same. So, if we have the 4 of them pulling in 4 directions and Miles wins, the net force is going in Miles' direction. Now, we're going to try a little experiment.
Great.
Let's